All right, so let's just recap a bit of what we were doing in Chapter 4. So we talked about projectile motion. So I guess the idea here, the idea here is basically the x and y directions are decoupled. So you solve basically the horizontal and vertical components independently. Okay, so we've got our sort of 5 equations of motion that we can use for constant acceleration. So the vertical component is just due to gravity. And then we worked out things like the equation of the path. So in this case, we eliminate the time variable. And if we look at the equation for the position and equation for the position in the x direction, position in the y direction, and then eliminate, and we can get an equation for the whole thing, for the whole path. Range is just, basically where it hits the ground again. So you work that out using when y is equal to 0. Okay, and then we did this one. And then I think this is where we got up to. So this is kind of a slightly different, type of movement, you might say. So uniform circular motion. So this is basically anything that is just going around in a circle. So, you might have encountered this already somewhere before, but you can derive things like the velocity and the acceleration in different ways, but in my opinion, again, it's actually very easy just to use calculus and to work out the position, velocity, acceleration. So I think this is actually the most straightforward way. I seem to remember some, ways of working out the, the relationship between the velocity and the acceleration. Using various methods, but like non-calculus methods. But I find it actually pretty not something you would easily come up with. Whereas the calculus method is just it's just generic and it always works and it just works simply. So let me just derive these equations just for uniform circular motion. So we're looking at something. Going in circle. So could you press F2? Yeah. So it's going in a circle. Okay. All right. And the position is going along the circle. And let's say it's going anti-clockwise. So it's going this way. And as we normally do, we define the angle to be the angle with respect to the x-axis, and then this is the positive direction, so this is positive theta. And the radius is r. Okay, and so firstly, this is uniform circular motion, so basically it just means that the angular velocity is constant, right? So, okay, technically speaking, we haven't really done this equation, but I mean, I think it's in a way straightforward enough. This is basically the angular version of, just distance is speed times time, right? So instead of the distance being speed times time, we've got this is the angular speed, so it's like radians per second or degrees per second. This is the time, and that's the number of degrees. And basically we're saying that this is constant, right? So this omega is just a number, and then so the relationship between the theta and time, basically theta just keeps on increasing constantly in time. And of course, an angle is periodic with 2 pi, so, so 2 pi, 4 pi, basically you reach the same point after 2 pi. So 2 pi is the same as theta equals 0. Okay, so that's the angle. And then just from trigonometry, we can simply just write down the coordinates of this by looking at that triangle. So the position vector, which I'm calling r here, I forget why I call it r, but anyway. So it's r cos theta, r sin theta. Just trigonometry. And we've said theta is omega t, so r cos omega t, r sin omega t. All right, and then basically the hard part is actually done now, and the rest you just throw into calculus and then, you know, don't think about it almost. So things like velocity, well, we know it's the derivative of the position, so just do calculus. Derivative of cos is minus sine, but it's omega, so we need a omega out here. Derivative of sine is cos, so this is r omega cos omega t. So that's our velocity vector, and it's good to write down which direction we're talking about. So this r vector is something that's obviously pointing that way, right? So it's just the distance. Well, here's the origin, here's the point, so it's pointing this way. Now, if you have a look at this one, it's got a minus sign here, so that means it's say this is in this first quadrant, right? Then this is actually pointing to the left, and this one is positive, so it's going up. So you can see that it's exactly in the direction that you expect it to be pointing. So the velocity, so the position vector is pointing this way, but then the velocity vector is pointing actually 90 degrees to this. And well, that's obvious from what's happening in this. It's swinging around, and so it's kind of obvious geometrically. But maybe the nice thing about here is that we didn't have to try and work that out or use any physics to figure out that it's going in this velocity. I just took the derivative and it just all comes out. Right? So it's easy. Just to show you that it really is perpendicular. So for example, if remember that we did the dot product, right? Dot product? What do we call it? Scalar product. Call it scalar product. So scalar product, when we do the scalar product of these two, remember that was equal to the velocity radius times cosine of the angle between them, right? So if the angle between them is 90 degrees, what is this going to be? Yeah, 0. Yeah. So it's 0 if theta is 90 degrees. And I've said it's perpendicular, so let's just check it. And so actually in this instance, it's not so convenient to use this formula because we'd have to work out that angle here, right? I guess I've already told you the answer that it's going to be 90, but say if you didn't know that, it would be actually way easier just to use the original definition of the dot product, which is the scalar product, which was, remember if you're doing a scalar product with B, it's like AX BX plus AY BY. Okay, so let's just do that with these two vectors. So here I'm going to get minus r squared omega sine omega t cos omega t. And here I'm going to get r squared omega sine omega t cos omega t. And you can see these are exactly the same. So it's 0, right? So, well, you can see that all the maths works quite beautifully, right? Now the magnitude of the velocity is just r omega, because so I've said the velocity is this, right? So from this vector, how do we work out the magnitude of this vector? Actually just on the screen there, but okay, maybe the word I'm looking for is just Pythagoras, right? So you just do Pythagoras on this. So if we want to work out the magnitude of the vector, it's going to be well, vx squared plus vy squared. So that's squared, so it's r squared omega squared sine squared omega t plus squared omega squared cosine squared t. And, sorry, square root. And then sine squared plus cosine is 1. So it's that, and then so it's half omega. Maybe it's also, you could also just no, sorry. Not sure if you could really immediately get it from there, actually. No. Okay, yeah, so in this case, I think this is the easiest way to get it. Okay, and then if you want the acceleration, then we can also take the derivative again. So the acceleration vector, we just look at the velocity vector and then just take the derivative. So what's the derivative of the x component here? Right, yeah. It's actually just on the screen. Negative omega squared cosine omega t, because sine becomes cos, and there's another omega that comes out. Here, cosine becomes sine, so sine omega t. And then the thing that you can see here is, sorry, put the omega squared in the wrong space. So let's pull out this factor of minus omega squared. Just factorizing out minus omega squared. What's this thing here?
Vector R.
Yeah, vector R. That's just vector R. It's exactly there. So the acceleration is actually just vector r multiplied by omega squared. It's also got a minus sign. So in terms of the direction of this thing, well, acceleration is actually going exactly the opposite direction to the position vector. So it's kind of interesting that, you have the position, you've got the position vector, but just from that you can work out the velocity acceleration just with calculus. But they all point in different directions, right? So I don't know. I mean, it seems kind of well, it's kind of interesting that they're all pointing in kind of different directions. Yet you can actually just simply derive it from calculus. All right, so we've got this relationship, and basically acceleration is pointing in the opposite direction up to some constant, and we can also relate it to, in terms of the magnitudes, we can relate it to the velocity in the acceleration, and maybe this is the formula that you often see. But all right, so let's first work out the magnitude of A. So magnitude of A vector. So this is just A without the vector symbol. So this thing is what's the magnitude of this thing here? Oh, okay. What's the magnitude of R vector? So magnitude of R vector is just R, right? And so I think what you're saying is, R squared. So in terms of magnitudes, so we're just looking at the sizes of these vectors. So A is related to R in terms of the magnitudes of vector in this way. But we also worked out down here that V is R omega. This is again just the magnitudes of the vectors. So we can let's get rid of omega instead of and write it in terms of V. So omega is actually V over R. So yes. So we're doing magnitudes, so there's no more minus. And this is going to be V squared over R squared, just putting in the omega times R, and so this is V squared over R. So we can relate the acceleration to the velocity in this way. Yeah, so here we've related acceleration to the kind of position, if you like, the radius. Here we've related it to the velocity, and this is relating the velocity to the radius. Yeah. Okay. All fine. Okay, good. So let's do this one. An object moves at constant speed along a circular path in a horizontal xy plane with the center at the origin. When the object is at -2 meters, its velocity is -4 meters per second in the y direction, j. Give the object's velocity and acceleration at y equals 2. Okay, so let's look at the velocity one first. Well, I think for this one you really need to do a little sketch and do it. So I'll give you a minute to work out what these two are. Okay, so okay, for A, what do you think? Who thinks A? And B, C, and D. Okay, all right. So let's draw a diagram. Object moves at constant speed along circle path. So origin, circular. Object is at -2 meters. Velocity is -4 meters per second J. So on this diagram, where is this talking about? Which point on the circle are we talking about here? This -2 and this -4J. Well, most of you seem to have got it right, so you must have some idea, right, of where this one is. So is it here? Do I have to do this? Here, 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 right. So you say it's here, okay? But we're not given a scale or anything. We're not given any radius of the circle. why couldn't it be somewhere over here? Why couldn't it be sort of somewhere like in between? Like we're not told what the y position is, right? All we're told is it's at x equals -2. It's not saying it's y equals 0, right? So why couldn't it? Why wouldn't it be like somewhere in the middle here? Yeah.
So the velocity's only pointing down.
Yeah. Exactly. Yeah. So because if you suppose it's here, then we don't know which. Okay. I suppose we can eventually work out which way it is, but here would be sort of diagonally pointing somewhere, right? But this is pointing exactly down, and this is at -2. So the only place where it's going to be pointing exactly down has to be just on this edge here. And so just from those two pieces of information, yeah, it has to be right on the edge here, right? So, because otherwise it wouldn't be pointing exactly down. And then from that we also work out that the radius is 2. So it doesn't tell you that the radius is 2, nor does it tell you that y is 0 or anything, but just you can still infer it from that, right? So this is, for velocity is 4, and the radius is 2. So we kind of work that out. And then the object's velocity at y equals 2. Okay, so I think once you've worked out that this is basically the crucial bit of information, and I think from the rest of it you can work it out pretty easily once you realize that. So at y equals 2, it's a circle, so obviously the radius is also 2 here, so 2 meters, that means it's up here, and we've already established it's pointing this way, so just following it up here, so it has to be going to the left there, and then the speed it can't change because it's uniform circular motion, and so it has to be b, right? Okay, and then what about the acceleration? Which one? A, B, C, D, B. Yeah, B, yes. So use that formula, this one. So V squared, A is V squared over R. We already worked out what the velocity is, 16. Sorry, velocity is 4. 4 squared is 16. 5 by 2 is 8. Then we just have to work out the direction, and we've worked out, we know from uniform circular motion that it's always in the opposite direction to the radius, right? To the radius position vector. So the position vector for up here is up this way, but the acceleration is always down. So it has to be b. Okay. Right, and then finally, maybe for what we'll do today is this relative motion. So this looks kind of trivial, but actually the questions that you do can often be kind of confusing. So it's kind of worth to get your sort of head on straight with this stuff. So firstly, so what are we talking about? We're basically talking about some object. So this is the object in question, some ball which we label by P, and there's like 2 frames of reference. There's, say, one frame which is over here, and we can consider for this example that this frame is just the frame of the ground, right? It's not moving. And consider another frame, which is the viewpoint of somebody in a car that's moving at a constant velocity. All right, so obviously these two people, so the person in frame A, person in frame B, would perceive everything about the position and velocity of the ball to be kind of different. From the point of view of frame A, and let's just say that this ball is not moving for the time being, then the object is just some distance away and it's not changing, right? Now, from the point of view of frame B, of course, you're in the car, so you're obviously getting closer to the object, or if you just view everything from your point of view, actually the ball is sort of coming towards you, right? Basically because you're getting closer to it. So basically what all this stuff is about is just to say, okay, so how do I translate things from one frame to another? So if I were to give you the coordinates of something in frame A, how do I work out what the coordinates are in frame B? And in this example, it's kind of trivial, right? So you just, for example, add them, right? So for example, x PA, what that means is that's the position of P, the object in question, according to frame A. Okay, so obviously that's just this distance from here to here, right? So just that distance. XPB is the position of P according to frame B. So that's that position from here to here. That distance from here to here. So just take that point in time, freeze frame it. The car's at some position. It's a bit closer to the object than the frame A, and so it's just that. Okay, and then there's also the position between frame A and frame B. Okay, so there's this distance, and so you can just see obviously from the diagram that if you add these two things, if you add that to the distance to that, then that's the total distance from A to B, so A to P, sorry, and then so you just add them and that's it. All right, so kind of pretty obvious, right? It's obvious, but basically if you get certain questions, you can actually kind of easily get confused somehow. So what I find in these types of problems associated with this kind of topic, you got to sort of be very clear about, what variable is what, because sort of everything looks like x, right? So that's x. This is x for you. This is x for me, and then some relative x, and then somehow you can just get it very all tangled up. So what I like to do is just to be very clear about the notation of these variables, right? So xpa, so I read that as position of P relative to A, right? And this is position of P relative to B, and this is position of frame B relative to frame A. And just be very clear about what that equation actually means, because once you have set up all your variables kind of correctly, then you can kind of relax and just leave it to the maths. It's a little bit like the uniform circular motion. The part that you really need to concentrate is to just get this initial definition right. And then once you got that right, you just put it into the maths and you let that take over, right? But if you're not careful about the definitions at the beginning, then you can mess things up. Okay, so we can once we're clear about our definitions, you can just sort of do something a little bit like what we did there, which is to calculate the relative velocities. Things burning. So the velocities, you just take the derivatives of the positions that we worked out. So, okay, fair enough. So you just take the velocity of the point relative to frame A, velocity of the point relative to frame B, and this is the relative velocity between B and A. This is taken to be a constant in this case. Likewise, you can just take another derivative, and that would be the acceleration. And in this case, the acceleration, we're assuming a constant velocity between the two frames. So in this case, the acceleration of BA, so A of acceleration of frame B relative to frame A, this is equal to 0. So in fact, the acceleration of the particle would be measured to be exactly the same for both frames. So you can read that as a statement. Observers on different frames of reference and move constant velocity relative to each other will measure the same acceleration. All right. And for 2D or even 3D, basically you just put a vector symbol on the top and it's all the same. Okay. Just as an aside, and this is not really part of the course, actually these formulas are not exactly true. So if you move at relativistic speeds, these formulas are not true. So, you know, what looks like an absolutely trivial and obvious thing is actually not even true. So if you were to try and take into account of relativity, then the exact formulas would look something like this. So the top part of this is basically the same. So this is the position of point in frame A. This is the position in point of frame B, and this is the velocity of the two frames. So this is velocity times time. So this is obviously just the like the same as the XAD that I had. But actually, there's some relativistic correction factor which goes because of relativity, and so in fact, this is not even exactly true. So if these are moving, then you would actually it would not follow this relation exactly. But because everything that we normally do is kind of at speeds which are way slower than the speed of light, this factor on the bottom here is pretty small. Any velocity that we're talking about is, this thing is very small, so it's going to be 1 minus some small number, which is almost 1, so you don't have to worry about it. And likewise with the velocity, in fact, it's not even quite as simple as taking the derivative of this. I think if you do a proper relativistic calculation, then it'll turn out to be this. So, okay, so even things which look absolutely trivial and obvious are not even that. So, well, that's physics for you. Okay, so do we have time to do this? Yeah, let's just leave this to the next lecture. That can be a good revision to just catch up on that. So, okay, so we'll leave it at today. But so today, sorry, not today, Sunday, we'll have a make-up day for Tuesday, right? So our next lecture will be Sunday. And was it group 4? Which group was presenting on Sunday? I think it was group, yeah, okay. Yeah. Yeah, so I think, so in your group, some of the people are remote, is that right? Yeah, okay, so we'll have a slightly different setup. We'll do it all over Zoom and stuff, so yeah, okay. Okay, all right, so see you Sunday.